Hey everybody, welcome back to another Robison rant. And yeah, let's get at it. So in front of you, I have a problem. If the source is oscillating at 8 cosine of 20,000 t, find the expressions for the current flowing through each of the branches. And while we're at it, we can also find the potential jump across the source. So go ahead, take a minute, see if you can hack through it. Okay. Alrighty then. Let's get at this sucker. So the first thing I'm going to do is rather than treating it as a cosine of time, I am going to transfer into what's called the frequency domain. That's where we use Euler's relation in order to introduce that imaginary component. And then we can think of this source as simply being the projection of a unit circle onto the real axis. Okay. So we basically can take this source that's oscillatory and start thinking about it as a rotation. And so we will go ahead, let's go ahead and write the source as this rotating vector, if you will, in the complex plane. So I will write it 8, the magnitude stays the same. And essentially what I do is I'll write it as e to the j omega t. And here I'm using omega as being equal to 2 times 10 to the 5th. So the value that's given in the body of the problem. Okay. Well, because I have now transferred this into the frequency domain, since I'm using this idea, I can now, rather than thinking about each of the elements as resistors, capacitors, and inductors, like separate kind of components, if you will, I can now think of these all in terms of impedances, which is pretty helpful. So let's go ahead. Remember, what is the impedance of a resistor equal to? Yeah, just the resistance, okay, R. What that means is that it's in phase, okay? There's no imaginary component. Well, how about the impedance of an inductor? Yeah, good, good, good. You got J times omega L. Okay. Good. And since we have, why don't we go ahead? Since we have a value for omega and we have a value for L, we could rewrite this. This is J times 2 times 10 to the 5th, L being 40, and then 10 to the negative 6th. Okay. And so you can see at the end of the day, 10 to the 5th, we get an extra 10 to the 6th right there from the 40 and the 10 to the 6th. And so we end up with something like 8J. Well, let's complete it for sake of completeness. Let's go ahead. What is the impedance of a capacitor? Yeah, and here we have a negative J over omega C. Okay, and so let's go ahead and figure out that value, negative J. And again, we have 1 times 10 to the negative 6. There's my microfarads times 2, and we have 10 to the 5th. And so at the end of the day, we get 1 divided by 0.2. That is 5. And we see because the component or the impedance of the inductor and the capacitor involve J's, they have the imaginary number in there, we would say that it's pi over 2 out of phase with the current. In other words, if the current, you could think of it as the unit circle, if the current is 100% in the real axis direction, then the impedance of the capacitor and the impedance of the inductor will be 90 degrees to that. And that's what the purpose of that J is in there. Okay, so now we have our impedances. So we can go ahead and attack this problem however we want. If we want to use KVL and KCL, if we wanted to do node voltage, we are free to choose at this point. Okay, well, for sake of argument, yeah, I don't really have a preference. Well, let's go ahead and do node voltage. Okay. Just picking something. So let's go ahead and ground this bottom one. And so I will write the voltage for the top. That is simply IS. And then we have plus the potential divided by the impedance of the 10 ohm resistor, plus the potential divided by the impedance of the 6 ohm resistor. I guess I'll call this R1 and R2. Plus the impedance of the inductor. And then added to that, we have the potential divided by the impedance of the capacitor. And that whole rigmarole equals 0. Well, we want to get V by itself. And so we have something that says the potential or the current source equals the potential at the node. And then we have all this rigmarole. Okay. Well, let's see here. We have 1 over 10. I'll go ahead and write this out for a moment. Plus 1 over 6 plus 8j. Okay. Plus, okay, 1 over z would be 1. Yeah, 1 over 5j. Negative. So I'll put a negative sign. Okay, well, let's go ahead. First of all, let's apply the complex conjugate to get the j's out of the denominator and into the numerator. Okay, I like doing that. So what do we have here? We have IS equals V. We have a 1/10 plus, we have a 6 minus 8j over 100. That's nice. Minus, oops, excuse me, this would be a plus 5j over 25. And now we're in a position where we can group our real and our imaginary terms. Okay. So let's go ahead. I have an IS equals V over, I'll put 10 over 100 here, plus 6 over 100. That's my real portion. And then added on to that, I have J times 5 over 25 minus 8 over 100. And so at the end of the day, IS equals my potential. What do I have here? I have 16 divided by 100, so that's 4/25 plus J times, oh, let's see. This is, I'll multiply by 4, so 20 minus 8, so that's 12 divided by 100. So that is 3/25. And so we're finally done. We have our voltage is simply equal to our current supply divided by 4 over 25 plus J 3 over 25. But not to be happy with the J in the denominator, let's go ahead and move it to the numerator. So again, I have a minus IS Guess we'll put 4 over 25 minus J 3 over 25, right? We're multiplying by the complex conjugate. And in the denominator, we get 16 plus 9, all divided by 25 squared. Right. Okay, well, let's see what that gives us. IS. So we have 16 plus 9 is 25. So that cancels out one of my 25s. And then I have 25s in the numerator and a 25 in the denominator. I should say it's a compound fraction. And so what I end up with is just simply IS 4 minus 3J equals my potential. But wait, there's more, right? This has just gotten us to the point where now I can substitute in my expression for the current supply. I have 8 e to the j omega t 4 minus j 3. So I'll go ahead and write that out. Let's go ahead and write this whole thing out. I'm going to just separate off right here. Okay. So what do I have? I have v equals negative 8, and then I have cosine of omega t plus j sine of omega t. And I want to multiply that by 4 minus 3j. And then don't forget that at the end, I want to throw out anything that has an imaginary number with it. And so we can see that the cosine is going to get multiplied by 4, and the sine is going to get multiplied by that 3. The other two terms, the cosine times the 3j and the sine times the 4, those will have imaginary components, and so we'll throw those out. So we're not worried about those at all. So what do we have at the end of the day? We have something that says, let's see, negative 32 cosine of omega t negative. Okay. And then at the end of the day, I have a sine of omega t here. So there is the expression for the potential drop across the source, or maybe I should say the potential jump across the source. Pretty nifty, huh? But wait, there's more, right? I still have to find the currents. Well, we'll say the current through the 10 ohm resistor, what I called R1, that's pretty straightforward. We take V, we divide by R1. Okay. I guess you could say the impedance, right? Technically, I should do V divided by the impedance. I should take this sucker right here and divide by the impedance, Z R1. Okay. But fortunately, the impedance of a resistor is real, and so the only thing I need to do is take the real part of the potential and divide by R. You could put the imaginary part in, but because R is purely real, that imaginary part won't change at all. And so what I end up with is something like negative 3.2 cosine of omega t minus 2.4 sine of omega t. Ta-da! Now let's take that in contrast to a different situation. Okay? What about for the capacitor? Remember that the impedance of the capacitor was negative 5J. And so we can't just take the real part of the potential anymore. So let's get an idea here. The current of the capacitor would be the potential divided by the impedance. And here the potential, again, just to remind you, was negative 8 e to the j omega t 4 minus 3j. Okay. And now I'll have to divide that all by negative 5j. And hopefully now you see what happens. The presence of this j in the denominator means that it's going to change the real and imaginary components in the numerator. In fact, if we want to move the j up to the top, let's just multiply both numerator and denominator by negative j. So now we're home free. We have something that says 8 e to the j omega t. And I have a 3j squared, j squared being negative 1, and I'll cancel with the negative 1 out front. So I just get 3 plus 4j, all divided by 5. Now we can finally throw out the imaginary parts, right? Let's get rid of the imaginary parts. And we have something that says IC is equal to, let's see here, we have the negative 8 over 5, 3 cosine of omega t. Okay. And then we have a 4j times j sine. So we'll have a negative 4 sine of omega t. So you can see how the presence of having that j in the denominator changes, you know, which goes with which here. Well, we might as well, for completeness, get the third current. Okay. The third current, the one running through R2, was V divided by the impedance of R2 plus the impedance of the inductor. Okay. And so again, we have something that says negative 8 e to the j omega t divided by 6 plus 8j. And so again, what we need to do is multiply both top and bottom by the complex conjugate. And what we end up with, we have our negative 8 still floating out around front, j omega t, 6 minus 8j, all over 100. And again, we're home free. Let's go ahead, expand e to the j omega t in terms of Euler's relation, perform the multiplication process, and throw out the imaginary pieces. So we have negative 8 over 100 times 6 cosine of omega t plus 8 sine of omega t. And there we go. There is our current running through R2. Pretty cool, huh? Now, the next question I think we should ask ourselves is, what happens if we chose to do this using instead phasors? And those relationships that we discussed last time, right? Now, don't forget, let me remind you, if you have a phasor, there's some magnitude, and I'll put in a direction. Don't forget that what that really means is you could think of that as being the magnitude multiplying e to the j omega t plus the direction. And I should say the initial direction. Okay, I put direction, I should have put phase. And so it shouldn't be that big of a surprise that when you take two phasors and do the division, it simply gives you the difference in the two angle measurements. When you divide two numbers with the same base, you subtract the exponents. So that's what's happening right up here. Or you know that when you have two numbers and you divide them, you know, the magnitudes would just divide. So, okay, so what happens if we want to do this in terms of phasors? Well, first of all, let's go ahead and write our current. Originally, we had our current as 8 cosine of omega t. We could rewrite that as 8e to the j omega t. Or if we're really lazy and just want to write it in phasor notation, we just write this as 8, 0, right? Because I'm adding 0 up here in the exponent. So 8, 0 degrees. Well, let's go ahead and write down the phasor relationships for our resistor. Remember that our impedance it's written as R, and that means there's no imaginary piece. There's only strictly a real piece. And so what I could write this as is the magnitude of R times 0 again. And this is what we mean by the resistor is always in phase. Well, for the inductor, we wrote that as 8. I believe we had an 8J for the impedance of the inductor. Yes. And so we could rewrite that. This one points purely in the imaginary direction. So we could write that as 8, or if you prefer the inductor value, 8, and the purely imaginary direction is 90 degrees. Okay, well, how about the impedance of the capacitor? That's negative 5J. And so we could write that as pointing purely in the negative imaginary direction. So we'll say 5, negative 90. Good so far? Now we'll have to flip-flop between these kind of two representations. And the reason for it is that this right representation, the phasors, are really helpful when we're doing divisions and multiplications. Whereas these phasors on these expressions on the left-hand side in terms of real numbers and imaginary numbers is far more helpful when we have to do addition. And so you'll see I'll run it in terms of phasors, but through the course of the problem, we're going to have to do addition, we're going to have to do multiplication. So we're going to end up jumping between the two. Okay, that's just the nature of it. In fact, why don't I go ahead and do the one that we're going to have to worry about. We have this R2 plus J omega L. Okay, in that branch with the parallel capacitor, or excuse me, resistor and inductor. Okay. So if we wanted to do that one, what we should write, this is equal to 6 plus 8J. So let's go ahead and get the phasor representation for that. And this one, you're not going to be able to look at it and just know. You're going to have to actually plot it out. RE. You're going to have to plot it out. We're going to have to get our calculator out and figure it out. So it's 6 in the real direction. 1, 2, 3, 4, 5, 6. And it's 8 in the imaginary. 1, 2, 3, 4, 5, 6, 7, 8. And so we have a location in space that is 6 in the real direction, 8 in the imaginary. And again, we find the magnitude by taking the 6 squared and the 8 squared. So that's the length of our arrow. So the magnitude's going to be 10. And the angle is going to be simply the inverse tangent of the imaginary component divided by the real. Again, we're looking for this angle theta. So what do I have? Unless, you know what, I don't trust me there. Let's just do it again real fast. 8 divided by 6. I have 53 degrees. So the phasor for this vector, if you will be 10, 53.1 degrees. Good so far? Right. Okay, so let's go ahead and solve this sucker using phasors instead. So what do we have? We have that our current is given by 8, 0, and this is equal to our potential divided by 10, 0 plus 1 over 10, 53 plus 1 over 5, negative 90. Right, I'm just substituting in each of these phasors instead of the Cartesian representation of the impedances, if you will. Okay. So this is really what we're dealing with here. Now you could think of 1 as a real number, right? These are all, the 1 is real. And so we could rewrite this as simply, let's see, 1/10. So we still have that 1/10. And with a phasor of 0. 0 minus 0 gives me 0. Then we have plus 1/10, negative 53 degrees. And then we have plus 1/5 times 90. Right? So you see how I can do that division just really quickly. Just move the phasor, or the angle, the top angle minus the lower angle. You can think of this as 1 times 0 if you need to. Well, okay. What does that get me? Well, now unfortunately, because I want to do the addition, okay, I'm going to have to turn it back into reals for a minute, or like the Cartesian coordinates, the real and the imaginary components. Let's go ahead and multiply everything by 10. So I have 8, get rid of that denominator. So I have 80 times 0 equals this v, and what I have is 1 at an angle of 0 plus 1 at an angle of negative 53 plus 2 at an angle of 90. Well, let's go ahead and plot that out. Okay. So what I have here, this is the real, this is the imaginary. I have 1 at an angle of 0. So we'll just plot this. We'll say that's 1. There we go. I have 2. So 1, 2 at an angle of 90. Means I've got that sucker. And then I've got 1 at an angle of roughly 50 degrees, 53 degrees. So I'm going to have to add these 3 together. Okay. Well, let's get the resulting idea. This would be 1 plus 1 cosine of negative 53 plus, oh, you should yell at me, negative 53. I wrote that in the wrong direction. You caught it already. It should be down here. There we go. That's better. Plus 1j sine of negative 53, okay, plus 2j, right? 90 degrees is straight up. So what do we get at the end of the day? Here we get 1 plus cosine of 53, okay, plus 2 minus sine of 53. And I'm using those even odd properties of sines and cosines. Okay. And then why don't we go ahead and turn this back into a phasor? So now we have it back in its component form, if you will. But let's find the magnitude of this. So the magnitude would simply be 1 plus cosine of 53 quantity squared plus 2 minus sine of 53 quantity squared, and then take the square root. I sure hope that works. And what I get here is a magnitude of 2. That's amazing. I'm going to actually double check that. And I'm sure that I wouldn't be as surprised if I had worked this whole thing in terms of variables. Yep. So it's a magnitude of 2. Sweet. And we can get the angle as well. The angle is simply the inverse tangent of the imaginary component divided by the real component. Excuse me, that's a cosine. And so let's get that while we're at it. And so I get 36 degrees, 36.9 degrees. So what do we have now? We have the current supply, 80 at 0, equals V times the phasor 2 at 36.9 degrees. And now, hopefully you see, V equals, and this is where the phasor stuff really shines, right? Allows us to do these types of calculations particularly quickly. We get that the potential is 40 at an angle of negative 36.9. And, okay, well, let's now go ahead and find our values of our currents. Well, if I use my phasor relationships, 6.9 divided by 10 at 0, I get 4 times 36.9 negative. Or if I want it for my capacitor, again, it would be the phase of the supply, the potential at the node, divided by the phasor for my capacitor. So 5 negative 90. There we go. 5 times negative 90. Oh, shoot. So we get 36.9 plus 90, right? Okay. So we get something like 8 times 53.1. Or if we want the current flowing through R2, we have 40 negative 36.9 divided by, and I don't remember what we had for the phasor there again, 1053.1. So we have 10 and 53.1. And so here you get something like 4 at negative 90. Boom. Pretty cool, right? And for completeness, let's go back and double check. Okay. So let's take, for example, this original expression that we had right here. Okay. And we see that, okay, well, we also had this 3.2 cosine, excuse me, cosine of omega t plus 2.4 sine of omega t. So theoretically, these two representations are the exact same. And I know it doesn't look like that. I had to actually convince myself that this works. So let's go ahead and, so that you don't take my word for it, that you actually see it, let's go ahead and look and see that these two representations are actually the same. Okay? Here we go. So what we had was something that said 4 times the phasor of 36.9. Okay? So I guess there's a negative 36.9, so I've dropped a negative sign somewhere. We'll find it later. Okay? So, well, let's rewrite this. Let's go back. And remember that this is essentially writing this, e to the j omega t minus 36.9. So we'll leave that there. Okay. But now I'm going to break this up. I'm going to call this 4e to the j times negative 36.9. Okay. And then I'll put e to the j omega t here. And now let's go ahead. I'm going to apply Euler to both of these expressions. So I get 4 cosine of 36.9 minus j sine of 36.9. Again, I'm using that idea of even and odd functions. And I multiply that by cosine of omega t plus j sine of omega t. And now let's go ahead and FOIL and throw out the imaginary pieces. So I have 4 cosine of 36.9 cosine of omega t plus 4 sine of 36.9 sine of omega t. Now go ahead, check it in your calculator. What value do you get when you take 4 times cosine of 36.9? Yeah, you should have gotten 3.2. And go ahead, check me. 4 times sine of 36.9. Yeah, you got it again. It should have been 2.4. So what you end up with is that 3.2 times that 2.4. So it works out. It's pretty cool, huh? What I want to show you is that this phasor representation leads to the exact same thing. Okay? And the only reason that this phasor representation is even introduced is that it makes these calculations of division and multiplication easier. Okay? You don't actually need to do it. Okay? You could leave it in terms of real and imaginary numbers, and it just makes the algebra a little more arduous to work through. Not impossible, just takes a little bit more time. Okay? Well, my intention was to include a couple of other examples here, but I think this is probably a good place to stop, and we'll get some more example videos going. But for right now, I think that's sufficient just for completeness and not letting this video get too long. So in any case, stay tuned for more examples. Thanks for your attention. Keep working hard, and I'll see you next time.